This is chapter 10 for C2 and it's based on trig identities and solving simple equations. At the end of this chapter, you should know these relationships. Tan theta is equal to sine theta over cos theta. That's not given, so you have to memorise it. And sine squared theta plus cos squared theta is also equal to 1. We'll also go on and involve trig equations, and that follows on from chapter 8, and then some more complex trig equations where we've got some sort of transformation on the sine, the cos or the tan graph. So starting with the unit circle and some identities that we're going to come across. This one here is the tan theta is equal to sine theta over cos theta. That's not given, so you must memorise this one. And that's what's called a trig identity. The unit circle, which we came across before when we did the circles, or just the equation of a circle, you can see here if I drop a perpendicular from P, we get a right angle triangle, and from using our GCSE trigonometry, the SOHCAHTOA, so we're looking at SO, Ca and TOA, we can see here that we can find sine theta as the opposite over hypotenuse, cos theta as adjacent over hypotenuse. So this is your x and this is your y. So just using that little right angle triangle, we can find the ratios for sine, cos and tan. Then if we decide to define the loci of P, so it's the point on the circumference of a circle, then we can say that applying Pythagoras' theorem, we get x squared plus y squared is equal to r squared. And if we say it's a unit circle, then that means that the radius is equal to 1. So x squared, if we rearrange the cos theta, we get r cos theta is equal to x. And for y, we get r sine theta is equal to y. So if we put that into Pythagoras' theorem, we get x squared, which is r squared cos squared theta, plus y squared, which is r squared sine squared theta, is equal to r squared. So if we take out cos squared theta, take out the common factor of r squared, plus sine squared theta equals r squared. Divide through by r squared, and that's equal to 1. So r doesn't necessarily have to be 1, because you can see from that little proof there that the r squares actually cancel out. This is another identity. It's not given, so you've got to memorise this one as well. So we're going to use these identities and look at a couple of examples. Simplify the following expressions. If we look at the first one, sine squared 3 theta plus cos squared 3 theta, that's actually just equal to 1 because it follows the pattern of a cos squared plus a sine squared equals 1. As long as this angle here and here are the same, so if they are the same angle, then you can say that it is equal to 1. Looking at B, we've got 5 minus 5 sine squared theta. So if I take a common factor of 5 out, I get 1 minus sine squared theta. And then thinking about cos squared theta plus sine squared theta equals 1. If I rearrange that, I get cos squared theta is equal to 1 minus sine squared theta. So I can actually replace 1 minus sine squared with cos squared theta. So we've simplified that. And then looking at the third one, part C, we've got sine 2 theta divided by the square root of 1 minus sine squared 2 theta. Well, we know that as long as the angles are the same, we can say cos squared 2 theta plus sine squared 2 theta is equal to 1. So if I say cos squared 2 theta is 1 minus sine squared 2 theta, and if I take the square root of both sides, I get cos 2 theta is equal to the square root of 1 minus sine squared 2 theta. So this becomes sine 2 theta, and then I can replace the denominator with cos 2 theta, and then we know sine over cos of the same angle is tan 2 theta. So that's getting us used to the two different identities that we've got, and it's just some algebraic manipulation. Moving on to the next page, we've got example 2, and we've got to show that the fraction on the left hand side is equal to 1 minus tan squared on the right hand side. You'll notice that we have 3 signs here, and that is the identical to, so it's the identity symbol, exactly equal to. So with an identity, we take one side or the other, and we usually take the side that we can do most with. So what I'm thinking is I will take the left hand side and I will try and do some algebra on it. Now, as you know, one of my favourites is dots, and we can see on the top line there we have got a dots. So it's going to be cos squared theta minus sine squared theta and cos squared theta plus sine squared theta. That's going to be our top line, and that's going to be over cos squared theta. Now, as we know, if we look at this here, that's actually equal to 1 using our trig identity from before. So that leaves us with, so this part here is equal to 1, so that leaves us with cos squared theta minus sine squared theta all over cos squared theta. Now we've got one term on the bottom. We could split this up so that we've got cos squared theta over cos squared theta minus sine squared theta over cos squared theta. So our first part is going to be 1, and then we know that sine theta over cos theta is equal to tan theta, so if we just square it, we're going to get tan squared theta, a sine squared over a cos squared. So again, that's an identity, and what we say is that's equal to the right hand side, so we've actually shown it. QED. Next example, example 3. Given that cos theta is minus 3/5 and that theta is reflex, find the value of A, sine theta, and B, tan theta. The key thing here that we used in chapter 8 was the sign of the actual ratio. So this ratio here is negative, and because we've got a reflex angle, we know that it must lie in between 180 and 360. But because the ratio is negative, that means it must be in the third quadrant. So if we can find out what that is, then it should be fairly straightforward. Now, using our sine squared equals cos squared, sine squared plus cos squared equals 1. So using sine squared theta plus cos squared theta is equal to 1. Just notice that sine squared theta is exactly the same as sine theta all squared. It's just the way that we actually write it. So we have got sine squared plus cos squared, which is minus 3/5 all squared, is equal to 1. So sine squared theta must be equal to 1 minus 9 over 25. So sine squared theta is equal to 16 over 25. Now, to find out what sine theta is, we have to take the square root of 16 over 25. In our quadrant system, if it's in the third quadrant, that's what we said from the beginning, because it's a reflex angle, so it must be in the third quadrant. So all Scottish teachers are clever, so actually sine is going to be negative as well. So we take the negative square root of this one, it's going to be minus 4/5. And then if we look at part B, we want to try and find tan. And tan theta is equal to sine theta over cos theta. We know both of these, so it's minus 4/5 divided by minus 3/5. So minus 4/5 multiplied by minus 5 over 3, which gives us 4 over 3. And that's using the identities that we have. Sine squared plus cos squared equals 1, and tan equals sine theta over cos theta. And working on another example, we have got an obtuse angle this time. So given that sine alpha is equal to 2/5 and alpha is obtuse, find the exact value of cos alpha. So if we think about obtuse, that's going to be between 90 degrees and 180. So that's in the second quadrant. And we know that must be true because the sine ratio is positive. So it's going to lie in the second quadrant. But what we can do is, because we know that sine of alpha is equal to opposite over hypotenuse, we can draw a little right angle triangle, and that will help us find the exact value of cos. Because if cos is in the second quadrant, it's going to have a negative value. So if we make this alpha, we know it's not acute, but we can work it out from a little right angle triangle. And the opposite is 2, and we've got 5. So we can work out the shorter side by applying Pythagoras' theorem. So we have, let's call this A. So A squared is equal to 5 squared minus 2 squared. A squared is equal to 25, take away 4. So A is equal to the square root of 21. So that's equal to root 21. So from this we can get the cos of alpha, which is equal to the adjacent over the hypotenuse. so that's equal to root 21 over 5. But because it's in the second quadrant, all the ratios are positive, sine's positive, tan and cos. That means that cos is negative in the second quadrant, so we must give this a negative sign. So it's negative root 21 over 5. So that brings together all your GCSE work on right angle triangles. And our keywords of obtuse, and then looking at the sine ratio being positive, so that means that it must be in the second quadrant. Moving on to the last example before exercise 10a. Right, given that p is equal to 3 cos theta and q is 2 sine theta, show that 4p squared plus 9q squared is equal to 36. So, let's take p equals 3 cos theta. And let's take q, which is equal to 2 sine theta. And we can rearrange these to get cos theta is equal to p divided by 3, and sine theta is equal to q divided by 2. If we use the identity, so using cos squared theta plus sine squared theta is equal to 1, we can substitute in p over 3 squared plus q over 2 all squared is equal to 1. So p squared over 9 plus q squared over 4 is equal to 1. And we've got to multiply by 36 because that's the lowest common multiple of 9 and 4. So that would give us 4p squared plus 9q squared is equal to 36. So again, we've shown that using our identities. So if we look at exercise 10a, questions that I would like you to give a go, have a try at, is question 1. Question, move this forward a little bit. Try question 5, maybe the first column, so that's the identities. And then question 6. That's the absolute bare minimum for this exercise. It does go on to question 10 as well. You could give that a go. If you spend 10-15 minutes on that, pause the video, try those questions, and then I will reveal the answers. And welcome back, and the answers to exercise 10a, if you have a look there. So question 1, and move a little bit forward so you can see the identities at the bottom there. For question 5, we've got question 6 if you had given that a go, and then the other ones as well. So just pause that to mark your own work, please, and see how you get on with that. We're now going to solve equations, and we've looked at this briefly in chapter 8 when we did the quadrant system. We're still going to use the quadrant system, and we can see here that we're asked to find solutions. So there's your clue, there's more than one answer, one angle here, and it's in the interval from 0 to 360. So we're going to use our calculator in degree mode. So you can see for the interval here, we're working in degrees. And we want to find solutions of sine theta is equal to 1/2. Right, the first thing that we do then is we say to ourselves, this ratio is positive. And if we look at our quadrant system, we know that all sine, tan and cos are positive in each of the quadrants. So this means that sine of a half, which is a positive ratio, must be in the first and second quadrants. So what we do is we use a calculator to find out what theta is. So theta is equal to the inverse sine of a half, and that will give us our principal value. So that will give us the acute angle with that theta makes with the x-axis, the horizontal. So theta is actually equal to 30 degrees. So I go to my diagram, that's 30 degrees there and 30 degrees there. And we start at 90, 0, 90, 180, 270 and 360. So to find these values of theta, it's equal to 30 degrees from the first quadrant, and on the second one is 180, take away 30 degrees. So the two angles that I've got that have a ratio of a half are 30 degrees and 150 degrees. And you can check that using your calculator and you should come out with the same answer of a half for both of them. So let's just recap on that. We want solutions. Sine theta is a half. The ratio is positive. If it's positive, it's in the first and the second quadrant. We do the inverse sine of a half to get our principal value, and this is the angle that it makes with the horizontal x-axis. We draw it into the first and the second quadrant, and then we do our calculations. So the two angles that we end up with are 30 degrees and 150 degrees in our quadrant diagram. Let's take this a bit further with example 7, and this time we look at the interval that we're working in, and we can see that we're still working in degrees from 0 to 360. So we're looking at positive angles here. If we look at 5 sine x is equal to minus 2, we've got to try and get sine x by itself, so it's equal to minus 2/5. Right, this ratio is here is negative, and when we draw a quadrant system, we know again all sine, tan and cos. So if the ratio is negative, that means it must be in the third and fourth quadrant. So the sign of the ratio tells us where the location of the angle, but then we ignore the sign and we get a principal value by taking inverse sine of 2/5. And that will give us the acute angle that we can use to find out from our quadrant system. And that happens to be 23.6 degrees. So do inverse sine of 2/5 and it's 23.6 degrees. So what we're going to have there is 23.6 in the third quadrant and 23.6 in the fourth quadrant. So the two angles that we're actually looking for, that's one, it's 180 plus 23, and the other one is 360 minus 23. So putting our angles in again, 90, 180, 270 and then back to 360. So the two angles, x is equal to 180 degrees plus the 23.6 because it's in the third quadrant, and it could also be 360 minus the 23.6 degrees. It's really important that you always measure from this horizontal line because that's your 180 degree line, 0 and 180. So a little bit before and a little bit after. And that works out to be 203.6 degrees and 336.4 degrees. Now we usually give our answers to three significant figures, so we'll say 204 degrees and 336 degrees to three significant figures. Watch out in the question, it will ask you for a degree of accuracy. So this is where a quadrant system, that's why I really had a lot of practice on it, because I knew that we're going to use it for these equations. Let's move on. Next example, example 8. Again, we notice that we've got to solve it in an interval, and it's also in degrees. So make sure your calculator is in degree mode. We're asked to solve cos of x is equal to root 3 over 2. Right, same scenario every single time. We look at the ratio, we see that the ratio is positive. We locate where the angle is going to be. All are positive in the first quadrant, only sine, then tan, and then cos. So that tells me that the angle must be in the first and fourth quadrants. We now have to find a principal value, or the little acute angle, and we're going from 0 right the way around to 360. So to find x, the principal value, it's equal to the inverse cos of root 3 upon 2. And that should be familiar to you as x being 30 degrees. So if we look at a quadrant system, 30 degrees in the first quadrant is here, and 30 degrees in the fourth quadrant is here. So x is equal to 30 degrees, or 360 minus 30 degrees, and that gives us two solutions of 30 degrees and 330 degrees. And if you put that into your calculator, if you do cos of 30 degrees, you'll get root 3 upon 2. If you do cos of 330 degrees, you'll also get root 3 upon 2. Now we've been working in degrees, we want to be able to work in radians as well. Look at the next one. We've got to find the values of theta in radians. Now if it doesn't state in radians, you can see from the interval here that indicates that we are actually working in radians. So we've got to satisfy this equation. Sine theta is equal to root 3 cos theta. We're going to have to use one of our identities, and we're going to use sine theta divided by cos theta is equal to tan theta, because we can't solve it as it stands just now. So if we divide everything through by cos theta, which we're allowed to do, it turns this one into tan theta is equal to root 3. Then we're back to the scenario again, that we have a positive ratio, and a positive ratio for tan means that it's going to be in the first quadrant, all sine tan, so that means it's going to be in the first and third quadrants. Now we're not working in degrees this time, we're working in radians, so it's 0, pi by 2, pi, 3 pi by 2, and 2 pi. So in radian mode on your calculator, to find theta, your principal value, theta is equal to the inverse tan of root 3. Your calculator will give theta as pi by 3. So on a diagram, pi by 3 is about there, it's about 60 degrees, and pi by 3 is there. So the two angles that we've got, pi by 3 is in the first quadrant, and then we need pi plus pi by 3 for the third quadrant. So altogether it's pi by 3 the first quadrant, and then for the second one it's 4 pi by 3. So in radian mode, if you pop that into your calculator, you'll find that those two angles will give you √3. Question I would like you to try, there's only a couple of questions actually on exercise 10b. Right, the first question is based on degrees. If you look there, there's your interval, so that's in degrees. And I'd like you to try the first column. Then move on, and the next one that I'd like you to try is question 3. So question 3, and this time, if you notice, all of them are working in radians. So I think if we try, I'll go for D, go for A, I'll go for C. Right, give yourself a good 15 minutes to do that. Pause the video, have a go using the identities if necessary, and then using the quadrant system as well. So I'll pause the video and then I'll reveal the answers on the next page. Welcome back, and the solutions here for exercise 10b. Can you check them? I've asked you to do the absolute bare minimum in the last exercise. You should really try some more. If you notice on question 3, if you can't do it in terms of pi, then answer in radians. They don't have C's on there, but you could actually put a C up there, or you could write it as 0.59 radians, as in rad. Right, some more equations to solve then. These type are quite common, and the thing that you've noticed this time doesn't seem to be much different. The interval is in degrees and it's from 0 to 360, so that's familiar. The only thing that is not familiar is this 3 theta. Thinking back to chapter 8, that means we've got a transformation of our cosine graph. And a normal cosine graph, as you know, looks like that. But what we've got here, the 3 theta, means we've got 3 times as many. So we can't just go from 360. The 3 theta means that our quadrant system, we've actually going to have to go round 3 times, and we'll have to actually go to 1080 degrees and find it out that way. So if we look at the ratio, so cos of 3 theta in degrees is 0.766. Same routine as before, we look at the ratio. The ratio is positive, so that tells me it must be in the first and fourth quadrants. Now drawing the quadrant system, we're going to have to go around this 3 times. So 0, go around this again, gives us 450, 540, 630, 720. We've got to go round again. So that's 810, 900, 990, 990, and then 1080. So that would be going round 3 times, and the key thing is that we are measuring from this horizontal every single time. And that's simply because we've got 3 theta, so we have to change from 0 to 360, from 0 to 1080. Let's get the principal value then. So the principal value, which is the acute angle, we're going to do 3 theta is equal to the inverse cos of 0.766 Right, so that means I'll actually take out the 3 theta. I'm just saying the principal value is this. So the value that we're going to use in our quadrant system is going to be 40 degrees. Okay, so 40 degrees in the first quadrant looks like that. And in the fourth quadrant it looks like that. Right, so how do we do this then? Well, we've got quite a few values that we can see here. When we go past, the first one is 40, then we'll go round again, so it'll be 360 add 40, then when we go round again it's 720 add on 40. So that's our 3 angles in the 3 revolutions, and then we've got 360 minus 40, then 720 minus 40, then 1080 minus 40. So we're going to get 6 angles altogether, which is what we would expect because we're getting 3 times as many answers. So 3 theta then, is what we were working with, is equal to 40 degrees. So I'll work with the first quadrant first of all, then 360 plus 40 degrees, and then 720 plus 40 degrees. So that's the first quadrant. And then we've also got the fourth quadrant, which is 360 minus 40 degrees. That's the first time round. The second time round it'd be 720 minus 40 degrees. And the third time round, 1080 minus 40 degrees. So 3 theta is going to be equal to 40, 400, 760, 320, 680 and 1040. So 6 answers altogether there, but we want the theta. So what we have to do is divide each of these by 3, and the answers that we're going to get, we'll take them to 3 significant figures, and I'm also going to put them in order as well. So we're going to get 13.3 degrees, and then we'll take the 320 as the next one, so that's 107 degrees, and then 133 degrees, 227, 253, and the last one 347 degrees. Now although I didn't put them in order in the row above, the line above, I've put them in order here. Okay, so taking that one, taking 40 divided by 3, then 320, then 400, 680, 70 and so on. So you might want to find, work in the first quadrant first of all, and then the fourth. It's up to you, or you can alternate back and forward. So it's 6 answers that you're looking for. And that's an exam type question that you'd be expected to work out values of theta to 3 significant figures. So it could be worth a good 6 marks, that one, if not more. Now we looked at graphs that had been transformed, and as you can see here, we have a transformation of the sine graph. So we're going to get 2 theta, we're going to get twice as many, so we have to do 2 theta in between plus 360 and minus 360 degrees. It's also been translated, so the translation is 35 degrees to the right and 0. So we're going to have to add that on at the end. So let's just see how we solve this one then. We have sine 2 theta minus 35 is equal to minus 1. Now our ratio is minus 1, but if we look on the sine graph, we can see that minus 1 happens at this part here, which is 270, and the same at here, that's actually minus 1 as well, at minus 90. That's the two that we have there for minus 1. Now it's a little bit trickier when we've actually got a maximum minimum value. We're better looking at the graph just to see where our two values are. Now that means we actually have to go up to plus 360 and minus 360. So there's going to be another value, or there could be another value as we go that way. So if we continue the graph on, it's going to come up and then go back down again. And that's to minus 360. And this is a graph of y equals sine of x, or sine of theta. So I'm using the graph this time rather than the quadrant system, because it lies right on the boundaries here. We can still use it, and I'll show you how we can do that as well. So that's our y, and that's at 0. So for 2 theta minus 35 degrees is the inverse sine of minus 1. And we can see from the graph there's two values that feed back to this, with this going from minus 360 to plus 360. So that's 360 there. That's our x-axis. So that would give us two values of minus 90 degrees and 270 degrees. And then we would just solve that for theta. So 2 theta is going to be minus 90 plus 35 degrees, and 270 plus 35 degrees. So 2 theta is equal to minus 55 degrees and 305. We then divide through by 2, and that will give us minus 27.5 degrees and 152.5 degrees. So we could have done it the same sort of way, except it was right on the boundary. So if we look at our quadrant system, we would have to go from 0 all the way around to 360. If we got the principal value of sine of 1 would be 90 degrees. So it tells me that it's in the third and the fourth quadrants for this one. So it's right on this boundary here. Put that in a different colour. So if it was a negative, so we know that tan's positive there and cos. So you can either go in that direction and get plus 270, or you can go in that direction and get minus 90. So that angle there is minus 90, and the angle there is 270. And how did I get that? I just said the inverse sine of 1, which was 90 degrees, gives me my principal value. So I knew that it was originally the ratio was negative, so it had to be in the third and the fourth quadrant. So there's two different ways of doing that one. As I say, it does become a little bit trickier when you've got this as a maximum minimum value. I think the graph is easier to use, but then again you can still use your quadrant system. So what I'd like you to do is, on exercise 10C, I want you to try as many as possible. So what I would suggest as a bare minimum, question 1, those 3 there. Question 2, we'll do A and B. And then on question 3, can you try part A? So as I said, that's the absolute bare minimum to solve these equations. Notice the interval. The interval in the first one is in degrees, so you're working in degree mode on your calculator. However, if you look further down, You'll find for question 3 that you are actually working in radians because your interval has been given, but you've also got minus angles as well. So you're looking for from 0, pi by 2 to pi, working in that direction, but you're also trying to work in this direction, which is minus pi by 2 and minus pi. So you're working in the top half going in an anti-clockwise direction, and the bottom half you're going in a clockwise direction. Right, it'll take you a good 10-15 minutes to do those questions. I'll pause the video, or you pause the video rather, and then I will reveal the answers to you. Welcome back, and the solutions to exercise 10C. If we look at question 1, you can pause it at this point if you want to. So as I was saying, question 1, have a look at the answers there. Pause it if you need to. Then moving forward, the solutions there. Can I also suggest that you go on to examsolutions.net. And look at the trig section there and go through some of the questions using the quadrant system and the graphs as well. Okay, last part then. Exactly the same sort of thing, solving these trig equations, except this time we're going to use the identities that we saw at the very beginning of the booklet. It forms a quadratic, and we know how to solve quadratics by factorising and solving from there. So let's have a go at example 12, please. We have solve for the interval from 0 to 360 degrees. So we know that we're working in degrees. And we have the first equation is 2 cos squared theta minus cos theta minus 1 equals 0. Now you could let cos theta equal x like we have before when we've done our logarithmic equations, or you could see straight away that we can actually factorise it. So we get 2 cos theta here, cos theta, we get a 1 and a 1, that one must be a minus and a plus. So we factorise there, multiply it back out just to make sure that it's okay, which I think it is. So we get a couple of values. We get cos theta is equal to minus a half, or we get cos theta is equal to 1. Again, we've got cos theta equal to 1. It'd probably be better to draw the graph there to see what it looks like. And then on this one, we can find the principal value and use our quadrant system. So for cos equals a half, we look at the ratio. The ratio is negative, and if it's negative, that tells me that it must be in the second and third quadrants. So what we've got is something like this. So all sine, tan and cos. So we want to find our principal value that's associated with a half. So we do the inverse cos of a half, and the angle that's associated with that is 60 degrees. So for 60 degrees, it's in the second quadrant, so it looks like that. And it's in the third quadrant, 60 degrees. So theta for this one is going to be equal to 180 minus 60 degrees and 180 degrees plus 60 degrees. So theta is 120 degrees and 240 degrees. If you pop that into your calculator, you should get a ratio of minus a half. Now if we look at 1, I'm going to draw a graph of cosine going from 0 to 360. So there's 1, but 1's at 0. So you can see from the graph there that's 180 halfway. So from the graph we get theta must be equal to 0 degrees and 360 degrees. And it's allowed to equal either of those because the inequality's got unequal signs on it. Just be careful about that, because if you'd included 360 and that had just said less than, you would have lost an accuracy mark. So altogether we've got theta is equal to 0, 120 degrees, 240 degrees and 360 degrees for the quadratic that we've got. So you can see the merit in using both of these. It helps us out tremendously. Looking at part B, let's move this up a little bit. Hopefully we'll have enough room. So for part B, we've got sine squared theta minus 30 degrees is equal to a half. So if we want just sine of theta minus 30 degrees, we have to take the square root. So that's going to be plus or minus 1 over root 2. So we've got two equations that we have to solve. We've got sine theta minus 30 degrees equals plus 1 upon root 2, or we've also got sine theta minus 30 degrees is equal to minus 1 upon root 2. So that tells us it's in all the quadrants. So if we look at the first one here, we've got the ratio is positive. And if the ratio is positive, it's in the first and the second quadrant. If we look at the ratio here, the ratio is negative. So that tells me it must be in the third and fourth quadrant. So looking at the principal value, if we do the inverse sine of 1 upon root 2 to get our principal value, we get an angle of 45 degrees. So for the positive one, it's going to be in the first and the second quadrant, 45 degrees, going from 0, 90, 180, 270 and 360. And then if we look at the negative one, the angle that we've got there is in the third and fourth quadrant, so 45 degrees and 45 degrees, going from 0, 90, 180, 270 and 360, back down to 360. So that means that we can work out theta minus 30 degrees is equal to 45. Then it's 180 take away 45, which is 135. 180 plus 45, which is 225. And then 360 minus 45 is 315. And then what we've got to do is just work out theta, and that means adding 30 to each side. So the solutions we get are 75, 165, 255 and 345. And we've just got to make sure that it's within the range of 0 to 360. So watch out for the ones where you've got to take the square root, because then that puts it into all four quadrants. Last example before exercise 10D. Find the values of x in between the interval minus pi to plus pi. So that actually tells me that I'm working in radians. And to satisfy this equation. Now, as you can see at the top there, we're going to have to use this identity because we've got a cos squared and we've got a sine squared. We're going to change the cos squared because we've just got a sine x here, and that means that we can form a quadratic in sine only. So let's replace cos squared. Cos squared x is equal to 1 minus sine squared x. So if we substitute that in, we will get 2 times 1 minus sine squared x plus 9 sine x equals 3 sine squared x. We take everything over to the left hand side, or tidy it up, multiply it out. So 2 minus 2 sine squared x, 9 sine x is equal to 3 sine squared x. And I think everything over to the right hand side would be better. So we'll take the 0 there, and that means we've got 5 sine squared x, we've got a minus 9 sine x, and we've got a minus 2. This should factorise. We've got 5 as a prime number, so it has to be sine x, 5 sine x and sine x. And then we'll have a 2 and a 1, and that one's going to be minus, and that one's going to be plus. So we've got two solutions here. We've got sine x is going to be equal to minus a fifth, or we can have sine x equal to 2. Now, if sine x is equal to 2, that's a bit of a problem, because if you pop that into your calculator to get the principal value, it'll say math error. And that's all because your graph can only go up to 1 plus 1 or minus 1. So what we need to do there is say that that is not valid. Right, we're back to where we started again. We have a ratio, and that ratio is negative. If it's a negative ratio, it's going to be in the third and the fourth quadrant. So that tells me third and fourth quadrants. And then we'll find the principal value. So we'll find the principal value by doing the inverse sine of a fifth only, because that gives us the acute angle. And that works out to be, now remember you're in radians, and that works out to be 0.201 radians. So if it's in the third quadrant, we've got 0.201 here, and if it's in the fourth, it's 0.201 there. However, look at the interval. The interval is going from minus pi to 0, and then from 0 to pi. And what do we mean by that? So we start at 0, pi by 2, and then pi. And then we come round this way, so it's minus pi by 2, and then minus pi. So the actual angles that we want, that one and that one. So looking at what we have then, x is going to be equal to minus, because we're going in this direction, so that's negative angles. So minus 0.201, and the other one is minus pi plus 0.201. So x is equal to 0. It's either that, or you can do the other way of thinking about it is doing the minus of pi minus 0.201, if that makes more sense altogether. So the two angles that we've got are minus 0.201, and the other one is minus 2.94. And they're both in radians. And what you can do is just make sure your pi is actually 3.14159, but it will work it out for you just as a number. So again, 3 significant figures, that's what we'll work to, or whatever the question asks for. So this one was a little bit trickier, simply because we had the interval was positive angle and a negative angle, but also we're working in radians, so that's really quite tricky. And we were using our identity to change it into our quadratic and sine and solve it, and so on. So, exercise 10D. Questions absolute minimum that you should be heading for are question 1, the first column. If you can do the second column, that would be absolutely brilliant. And then exam type questions that we've got here. What I'd like you to do as many of those as possible, but your minimum would be 10, 11, 16 and 17. So can you do 10, 11, 16 and 17? I will pause now and you take a good 20-25 minutes to do these questions, and then I will reveal the answers to you. Welcome back, and the answers to 10D, you can see there the first few, and then if you pause the video you can check your answers there. And then looking at mixed exercise 10E, check your answers for that as well, please. And then on the next page we've got exam questions that I'd like you to hand in on file paper. We've got 5 questions altogether, and if you could get those done for next week, we'll say next week, and I'll catch up with you at some point. As I say, I'd also recommend looking at examsolutions.net for a few of these questions, especially exam type question. The ones that I like to put in especially are question 2, where you're having to manipulate the equation using the identities right at the very beginning.